Dynamic data sets involve a direct trade-off between merging and searching. While connecting nodes is a simple pointer assignment, keeping the search paths short becomes more difficult as the structure grows. Watch what happens when these nodes violently collide without a structural rule. In a naive disjoint set, the union operation blindly points the root of one element to the root of another. We are simply creating a sequential chain of merges. If we perform a sequence of unions, linking 1 to 2, 2 to 3, and so on, all the way down to 6, we observe a structural collapse. This uncontrolled vertical growth destroys the efficiency of the tree. Our dynamic tree has functionally degraded into a basic linked list. To locate node 6's root, the algorithm must traverse every single link, 6, 5, 4, 3, 2, 1. This results in a worst-case time complexity of theta of n. A linear time complexity is inefficient for massive dynamic graphs. If you are tracking a network of 10 million connected devices, tracing 10 million parent pointers for a single query will stall the operation. To scale this algorithm, we must engineer two specific heuristics. We need a preventative rule to govern how trees merge and a reactive rule to correct the structure when we search. Together, they will reduce this linear bottleneck to near constant time. Our first optimization is preventative. We call it union by rank, and its purpose is to stop trees from becoming deep during the merge phase. We achieve this by assigning an integer property called rank to every root node. As you can see by this vertical counter, rank acts as an upper bound estimate of the tree's total height. The rule of this optimization is strict. When merging two sets, you must always attach the root of the smaller rank tree as a child to the root of the larger rank tree. This pseudocode illustrates how the rule is applied. The conditional logic evaluates the ranks of the two roots before any pointers are reassigned. If the trees have unequal ranks, the algorithm forces the shorter tree to hide beneath the taller one. The shorter tree becomes a branch of the existing root. Because the smaller tree is entirely absorbed within the existing height of the taller tree, the overall maximum depth of the structure does not change. Therefore, the larger tree's rank counter remains the same. The only structural change occurs in the else branch, which handles the moment we attempt to merge two trees of strictly equal rank. In this equal rank scenario, attaching one tree below the other increases the total depth. We choose one root to absorb the other, and we increment that new root's rank counter by exactly 1. By forcing short trees to always attach below tall trees, we prevent linear chains. This structural heuristic guarantees that the tree's height will grow logarithmically, solving the first half of our problem. Let's trace how this balances a structure. We start with 4 distinct disconnected elements, each initialized with a rank of 0. We execute a union on 1 and 2. Node 1 absorbs 2, and its rank increments to 1. Next, we union 3 and 4. This is an independent operation with equal ranks. Node 3 absorbs 4, and its rank increments to 1. Now we hit the test case, merging set 1 with set 3. Both roots share an equal rank of 1. Following our rule, node 1 absorbs node 3. The structure shifts into a balanced pyramid, and node 1's rank increments to 2.
Compare this shallow pyramid to the vertical linked list we generated in our naive approach. The depth is contained. Because the depth only increases when two trees of equal size merge, the maximum height of the tree will never exceed the base 2 logarithm of the total number of nodes. The worst-case search time is now big O of log n. Bounding a search to logarithmic time is a significant improvement. However, traversing even a shallow tree multiple times still consumes cycles. To reach maximum efficiency, we must target the find operation itself. This brings us to the second optimization, path compression. This is a reactive heuristic, meaning it flattens the structure as a side effect of querying the data. In the optimized find function, the code intervenes directly during the variable assignment. setting the parent of x equal to the result of the find operation. The core trick is that the code intercepts the return value of the recursive call. As the function traces back up the tree, it uses that ultimate root value to rewrite the pointers of every node it touches. Let's execute this on a deep, unoptimized path from node 5 up to node 1. We initiate a find operation on node 5. The recursion travels downward, calling find on 4, then 3, then 2, until it hits the root. Finding the root is only half the operation. The real mechanics trigger as the recursion returns up the stack. We assign that root value to the parent of every node on the return trip. Nodes 5, 4, and 3 reconnect directly to the root. The mechanical result is a flattened graph. Every node visited during that search now points directly to the root. Calling find on any of those previously deep nodes will now resolve in exactly one step. Path compression sacrifices a small amount of overhead during a single deep search to permanently flatten the path. This ensures all future operations on that path are nearly instantaneous. We now have two forces acting on our data. Union by rank balances the structure from the top down, while path compression flattens it from the bottom up. Because a single find operation simplifies the structure for all subsequent operations, we use amortized complexity. This averages the expensive and cheap steps over a long sequence of operations. When you evaluate the combined effect of these two heuristics, the amortized time complexity is big O of alpha of n. Alpha of n represents the inverse Ackermann function. The standard Ackermann function grows rapidly, meaning its inverse grows extremely slowly. In computer science, it is considered one of the flattest curves possible. With an n value of 10, the inverse Ackermann output is less than 4. Scaled to 1 million nodes, it remains under 5. Even if n equals the atoms in the universe, the output is still less than 5. For all practical engineering, alpha of n is a constant. The amortized complexity is effectively O of 1. This efficiency allows Kruskal's minimum spanning tree algorithm to scale to graphs with millions of edges. By keeping our search times near constant, we prevent cycle detection from becoming the ultimate bottleneck in large-scale network analysis. Applying these two heuristics changes the structure of the data itself. We move from a linear worst case to a near-constant amortized time complexity, ensuring the algorithm remains efficient regardless of the dataset size.